Here's another impact problem, problem 1581. Talks about a girl. She's throwing a ball at, from a height of 1.5 meters at 30-degree angle. Initial velocity is 10 meters per second. The ball flies 3 meters to a wall, impacts the wall, and comes back. And we want to find velocity at which it strikes the wall, B, point B, a velocity at which it rebounds from the wall, coefficient of restitution is 0.5, and distance from the wall to where it strikes the ground at C. So the problem has three parts. We need to find the components of the velocity right before it strikes or impacts the wall. And then we need to find the B, what will be the rebound velocity. And with those as initial conditions, we want to find where the ball goes and gets back to the ground level. I chose a reference frame with X, horizontal axis, the ground level, and origin is where the person is. So what do we have? We have for phase one, motion towards the wall, we have velocity in the y direction at A of A. So let me use this kind of thing. Velocity A in the y direction, velocity of A in the x direction. Okay, and these are 0. Now we know that if we assume a combination of vertical and horizontal motion, the horizontal motion, neglecting air drag, it would be constant velocity. The vertical motion will be a constant acceleration motion, negative acceleration down, equal to acceleration to gravity. Okay, so part A, initial flight. So we know velocity of A in the x direction, 0 is going to be VA 10 meters per second times cosine of 30 degrees. So that's 10 times cosine 30, that's 8.66 meters per second. Velocity of ball A in the y direction initially, that's VA times sine of 30 degrees, and that's equal to 5 meters per second. Sine of 30 degrees is 1/2. And then we're going to state the constant velocity motion in the horizontal direction. So, and so we have displacement. I call this x to the wall, xw. So xw is going to be velocity of A in the x direction, 0 times t, from where we can calculate t. And then I have let's call this y of impact, although we have a point B, so we can call it yb. That's point B. And this one could have been, instead of, so let's call this yb and xb, okay. So I have y of b is going to be initial y0 plus velocity of A in the y direction, 0 times t minus 1/2 g t squared. Okay, so from the first equation, we can extract t. T is going to be xb over velocity of A x0, that is, so xb is 3 meters over 8.66, and we have it time is 0.346346 seconds. Okay, I'm taking this time value, I plug it into into the second equation. And so what do we have? We have 1.5. This is VA, and this is 5. And this is, of course, 9.81. So with this, we get the height of impact, that is y of b, is 2.643 meters. Okay, useful information for phase 3 of the analysis. But for the phase B of the analysis, I need to find rather initial flight and what does it say? Velocity at which it strikes the wall. Okay, so I need to find the velocity. It will be velocity of A in the x direction before impact. This is velocity in the of A in the y direction before impact. And I can, so based on the earlier conversation, I can tell velocity in the A direction of A in the x direction right before impact. It's VAX0 is 8.66 meters per second. Yes, and then to get the velocity of A right before impact in the y direction, we need to state the velocity with constant acceleration. It's the equation v0 plus a constant formula on the back cover. So v is v0 plus a constant times t. So it's going to be velocity of a in the y direction 0 minus gt. And we have t, so we can calculate v right away. It's going to be, so VA0 is 5 minus 9.81 multiplied by the time 0.346. Okay, so what does that equal to? It's 1.606. 1.606 meters. Okay, rather meter per second, I'm sorry. So if you're to calculate the velocity at which it strikes the wall, you need to, since your orthogonal components, velocity of A right before striking the wall, square root of VAX1 squared plus VAY1 squared. And so I have the values like this one and this one. I squared them, and it looks like it's 8.81 meters per second. Okay, this is the answer for part A. Part B now, that's the impact. And we have impact. We haven't done problems where impacting is with a wall. So that's assume infinite math. And linear momentum conservation is not going to help us because of the large mass, and we need to rely on the information about the coefficient of restitution. Coefficient of restitution would be velocity of the wall after impact minus velocity of A in the x direction after impact over velocity of the ball A in the x direction before impact minus velocity of the wall before impact. Now these are 0, and and this is equal to 2.5 as stated in the problem. So I have 0.5 equals negative velocity of A in the x direction right after impact over velocity of A in the x direction right before impact. So this is, and I have VAX1, VAX1, it's, so from here I get VAX2 is negative half of, that is 0.5 times 8.66, or negative 4.33 meters per second. So this is the rebound velocity in the x direction. Okay, so I have VAX2, and this is 4.33 meters per second, and it points backwards. The negative means this is in the negative direction of x. The velocity of the ball after impact in the y direction is the same as before. There's no friction. Assume there's no friction, so velocity is conserved. So AY after impact equals velocity of A in the y direction before impact. So we have now part, let me just add this. So velocity of A in the y direction after impact is just going to be velocity of A in the y direction right before impact. And this is 1.606 meters per second. If you want to calculate the magnitude, you do the same. You take the square root of the squared values. Okay, so for C now, we have, so that is part C of the problem. We need to look at the reverse motion. So we have the equations in Cartesian coordinates and gravitational field, and we want to find distance s. Okay, so that means we need to state the displacement in the x direction. So x will be, according to the figure, will be a negative value. So I'm going to call that point xc. Distance would be 3 plus the xc, the calculated value. So xc is this is constant velocity, constant velocity equation. So s equals s0 plus v0 t. So I have xc equals negative velocity of, so VAX2 negative VAX2 times t. This would be a new time value. And then I have y at c, it's 0. So y at c, which is 0, equals, now this is accelerated motion with negative g acceleration. So I have, let me just say that I missed here a term. So it's not the initial x0, it's actually going to be xb. So I have xb minus velocity, we said VAX2 times the new time, the other time, the return time. Okay, and in the y direction, I have y equals 0 at ground level equals y at point B, which we calculated. Y at point B is this one. And then I have plus the velocity after impact in the y direction is still positive. So it's going to be v of, well, I put a minus here. It means I'm taking the magnitude. Now, maybe if I put plus and use the negative 4.33, let's go this way and use the velocity with that sign for VAX2. Okay, so positive V AY2, this one here, times t minus 1 over 2 will be 1 over 2 g t squared. Okay, so again, this is a new t value. We're going to solve for t from this second equation, which is a quadratic, and of course we are going to take the positive time. So let's take the quadratic first. So it's going to be in moving everything to the right. I'm changing some signs. So it'll be half of 9.81 is going to be 4.905 times t squared. This term moved to the right. And then I have negative velocity of ay2, that's positive 4.33 times, I'm sorry, no, it's va2, so that's a positive, and it ends up negative by moving it to the right. So negative 1.606 times t, and then negative will be yb moved to the left, so I have yb 2.643 equals 0. Okay, so t is going to be 1.606 plus minus, and again we'll take the plus in front of square root of 1.606 squared minus 4 times, so it's 4 times 4.905 times 2.643. Okay, everything divided by 2 times 4.905, which is this one here, is 9.81. Back to the search to gravity. So again, take the positive t, and this is, I have the answer is 0.9158 seconds. Okay. So with this t value, we move to the first equation and calculate xc. This is xb, that's 3. Vx2, it's a negative value, so it'll be negative 4.33 times 0.9158 seconds. And this is negative 938 meters. So 938 meters, let's verify. So I have 3 minus 4.33 times 0.9185. 9185 equals a different value. So 3 minus 4.33, 9158. 9158. 9.9158 equals, okay, 9.65. Different values, different times. Okay, so let's assume this is the correct value. The distance that's required, s, now s is going to be 3 plus 0.938. So this is 3.938 meters. And this is the answer. Answer to be. I would emphasize again the essential part for B, the actual impact, that you use just the coefficient of restitution. I don't write the linear momentum conservation, because the mass of the wall, it's assumed infinity. So you cannot mix here like infinity times 0 in any way. There's a class of problems, I don't think this book has any, where you say this wall was instead the back of some camper van or a truck, and that's moving in one or the other directions. What you do for that kind of problems, you're analyzing so likewise, you write coefficient of restitution, but of course the wall is no longer going to have zero velocity. It has some velocity, and usually that's unchanged. So instead of 0 and 0, this will be some non-zero values. Again, you don't rely on the linear momentum conservation, because that's not going to hold. Wall is infinite mass. A van is very large mass comparable to a ball that strikes it. Okay, so this was another problem, and I'm going to post it on YouTube.